Okay, everyone's second favorite thing to hear about and talk about when we're talking about considerations in weaving is shrinkage. This is probably the hardest thing for me to understand when I was starting to learn all of this stuff. So if it is confusing for you, you are absolutely not alone. It's the worst. But it's really important to understand how it works. And it's really not that tough once you understand how to get there, basically. And you already understand a great deal about other math and how it all works together. So what we've already learned will help you to understand where we're going. So why does shrinkage happen? There's a lot of reasons for that. Certain fibers shrink more than others. Bamboo is really, really shrinky. Certain weave structures will shrink more than others. Unbalanced weave structures will shrink differently than balanced weave structures and in different directions and ways. And sometimes things pucker and sometimes things skew to one side, and sometimes you wash them and they get all crazy, but they're really, really tight. You know how when you put that wonderful cashmere sweater that your mom got you in the washer and it went and it turned into a Barbie sweater? That's shrinkage. We all know it and we all love it. We love to think about it when we're weaving because we don't want to end up with a Barbie napkin. So let's do a little bit of number work with some imaginary things that we're talking about real quick so that I can make a couple of points. Okay. What we have to do is something that is a little bit more complicated to get your brain around, I think. It's really hard for me, so if it's hard for you, I understand. But I think visually, thinking about it as a pie chart will help. But let's start with what we're talking about in the first place. We are going to divide by the reciprocal. So scary. You maybe have heard this before. It's probably been a really long time since you heard it, high school or before that. I also hadn't heard about it since probably freshman year of high school, maybe even earlier than that. But the way that this works basically is to take into account not the shrinkage rate itself, but what we're losing, if that makes sense. So, what we need to do to start is to consider a whole number. We're going to start with 100 because I like working with whole numbers. And let's say that my shrinkage percentage, my shrinkage rate is 15%. I'm pulling that number out of nowhere. It's just easy, so we're going to use it. So I'm going to take 100, which is my whole number, right? And I'm going to take 15 away from that. And I end up with 85. So thinking about it visually, if this whole circle here, if this whole pie equals up to 100, and this is 15, what do I have left? What I have left is 85. This is the reciprocal of my shrinkage rate. Does that make sense? Basically, I have the definition in our packet, which if you don't have, maybe consider grabbing. And it's basically two numbers that add together to make up a whole. But you only have one of those numbers. So you're trying to figure out what the other one is to make the whole, basically. It's way more complicated than that mathematically, but for our purposes, that's exactly what we need to know. Okay, so now that we have 85, what do we do with it? And the answer is we have to make 85 into a percentage. So 15 as a percentage is written like this. This is 15 as a percentage, 0.15. So what would 85 be as a percentage? Maybe 0.85. And that's exactly what it is. So you can either do it this way, to talk in whole numbers, which is what I like, that's what my brain likes, to talk about it in just big whole numbers. Or you can start with percentages at the very beginning of it if you want to. Then it would look something like this. Let's consider our whole pie to be just 1. And instead of 15 to 85, because clearly those do not add up to 1, it would be 0.15 and 0.85. So you can easily see how those two relate. This is just whole numbers for the sake of my brain. It makes me happy to think about these big whole numbers and how they make sense together. But if you want to talk about 1 and 0.15 and 0.85, then you don't have to worry about converting them later, but it's quite literally just as simple as adding a decimal right before that number. And that's how you get that. So now that we have this reciprocal number, how does that relate to the rest of it? All right, so I've done something with this, you can tell. So in order to calculate for the shrinkage, which is to say, if I want the end result of my project to be 20 inches wide, how much do I need it to be on the loom? How wide should it be on the loom so that when it shrinks down, I get it to about 20 inches? And the answer is divide by the reciprocal. So we'll take that number we got before, that 0.85. That was 15 taken away from 100. 100 minus 15 is 85. Make that a decimal. We have 0.85. This is our shrinkage reciprocal. I love that word. And now I'm going to divide those two. So we take this big number. This is what I want at the end of it. This is how wide I want it to be when I'm done, or darn close. And I'm going to divide that by 0.85. And I get a bigger number. And the reason that is, of course, is because we're dividing by a number that is less than the number that, or rather less than 1. And it gives us a bigger number. So what we should warp on the loom is 23.52. So just to explain a little bit, if we were to warp it up only 20 inches wide, we would get a number quite a lot less than 20 when we finish. Probably like 18 or something like that, because of the shrinkage rate of 15, which is not small. By dividing by the reciprocal, we get a really exact calculation of how big it should be on the loom to account for that shrinkage so that we end up with what we want. So we're going to warp on probably not 23.52 inches, but probably 23 and a half. So if I give myself 23 and a half inches on the loom, I'll end up with about 20 when it's washed. Okay, so we have more numbers. I know, they just keep coming. So we've already talked about shrinkage in our width. We were just talking about that. So what about in the length? Yes, indeed, things shrink in all directions. They don't just shrink in the width, they also shrink in the length, or in the weft as well as the warp and all this jazz. So what if we want to talk about shrinkage in the length? Well, we've done some more numbers, and I've done a bigger number this time so we can see how it affects it. I think these bigger numbers will kind of put it into perspective why this is so important. So 30% shrinkage rate, which is a lot. And this might seem like you never see it. Bamboo is really, really shrinky. And you know what else is really shrinky? Waffle weave is really, really shrinky. So these are things, just a couple of examples of things that shrink a lot in really different ways, and in ways you might not expect or plan for. And that's why sampling is so important. But since we know that our shrinkage rate is 30%, let's now figure out what our reciprocal percentage of that is and divide by the reciprocal. So 100, using this as our whole because I like big numbers, minus 30 gives us 70. So if we make 70 into a percentage, that's 0.70. Little pie chart for our reference here, another visualization. If this much is 30 and this is how much we shrink by, this is our reciprocal of that shrinkage rate. And this is what we're going to divide by, right? So let's say I want a project at the end of it, something crazy. I want 6 yards, which is a lot, but I want 6 yards at the end. So how much do I need to actually put on the loom at a 30% shrinkage rate to get that 6 yards when I'm done? 6 divided by 0.70 gives me a whopping 8.5 yards. That's a lot of difference. That's a whole 2.5 yards you weren't prepared for before we did this. So there are shortcuts that you can take. There are assumptions that you can make. There are, cares that you can throw out the window about, I'm not concerned if this ends up an inch shorter than I expected because of shrinkage. It's fine, it's fine. But in a situation where you're doing something like a waffle weave, or you're working with something like bamboo, and these things are really, really shrinky, you're going to want to consider that when you get done with your shrinkage, you're going to end up with a lot less than what you thought. So this is a situation in which you might want to do a divide by a reciprocal. again, like I had mentioned before with sampling, there is no weaving police that's going to come to your door and tell you if you don't divide by the reciprocal, you are not going to get what you want at the end. And it's not necessarily untrue. You may end up with a lot less than you think you are. But it's not the end of the world. I am going to let you in on a little secret. I have a sort of set length and kind of a general width that I shoot for when I make scarves all the time. Because I really don't mind if I end up with just a little bit less than I thought at the end, or if it shrinks up a little bit. Because it's just a scarf. As long as it's generally so long, just so that I don't end up with a scarf that's only this long, and just so that it's somewhat this wide, just so that it's not a skinny little narrow silly looking thing, I don't mind. It's not a precision project at that point. But if you're working in something, let's say a contest, like our weaving contest that we do, then maybe you want to shoot for the low end of the towel size. And what if it shrinks too much and you end up under that threshold? Wouldn't that stink? That's when this comes in handy. When you're looking for something, if you want to get, let's say you're doing a run of towels or a run of napkins or something like that, and you intend to get 4 out of it, but you didn't calculate for your shrinkage, so you end up with 3 1/4. And it's not very fun. It's not fun to put that sort of effort and time into warping up for what you think is going to be, say, 4 napkins. You only end up with 3 in a scrap. So that's why this sort of thing is important. You can get away with not doing it. If it's something that's not super critical, just add on a little bit extra. Maybe you go, nah, I'd like my scarf to be somewhere around 7 inches wide, which is a nice thick scarf. Maybe we go up to 8, and that'll be fine. It's a little less than 7, that's okay. And that's fine. When you're looking for precision, this is the way to do it. All right, so I had mentioned, I think before at some point, that I had done some samples for this whole project, and I have. These are really good illustrations of how things can change based on how you handle things, and how things can change based on how you decide to, whether or not your picks per inch and your ends per inch are the same, and how things change when you do them at different, dent sizes and things like that. So let's go ahead. I'm going to pick these up and we're going to show them to you and kind of explain why I chose to do that, and also talk about how to calculate the shrinkage rate. Because you may have something that you have done before and you go, okay, I know what it was before, I know what the dimensions were on the loom, and I know what the dimensions are off the loom. How do I make that shrinkage number? Where do I get that from? And we'll talk about that. All right, so lots of stuff on the board, but let's talk about these first. So here are my little samples, you can see them. Look at what happened to them in the wash. How the untwisted fringes just absolutely came apart. It's kind of sad, but it's actually a really good illustration of why you might want to twist fringes and why that's, maybe not so good for stuff that's going to take a lot of washing. Placemats and stuff like that, don't want a fringe on them, it's just not a good idea. Fringe disintegrates. So, I have done the same number of ends in all of my projects, all of my little samples here. It's the same warp. I just did one and then cut it off and rethreaded, and did one and cut it off and rethreaded, and that's how I did them. So I have one in 8 dent. Here's my 8 dent sample. There's a little close-up of that so you can see kind of how it turned out. It's very drapey. It's very loose. You can still see through it, so it's not very densely packed. You might hear the word sleazy used to describe this sort of look. And here is my 10 dent sample. So my little 10 dent sample is a little bit less open. It's definitely more dense than the one previous, the 8 dent, but it's definitely not packed in so tightly that it feels like cardboardy, It still has fairly nice drape. This is actually a really nice kind of in-between middle feeling. This is something I might enjoy as like a very lightweight shawl or scarf or something like that, but I wouldn't expect it to be particularly durable. So if you want durable, perhaps it is time to look at the 12 dent sample. Look how tiny. So this is, you can actually visually see more blue here in comparison to the rest of them. I think the variegated almost drowns it out, but you can see the blue very well here, and the variegated is not lost, which is great. But this is a nice, as far as everything goes, I mean, it's not super densely packed, it's not cardboardy, it still has some drape, but this is something that I may consider using for like like a table runner, which is actually, I'm gonna do a project for this later, and I think I am gonna do a table runner out of this. What's really interesting is that when I did these samples, I fully expected that the 10 dent would be the one that I wanted. And the reason that is because this is a DK weight yarn. And a DK weight yarn is, for those of you rigid heddle weavers, you know, is nice and comfy typically in a 10 dent heddle, 10 dent reed. I actually like the 12 the best. And it's not because the 10 is bad. It's not because the 10 isn't useful. It's just that this is the overall look that I actually want at the end. So that is just a really good example of why sampling is so important. It's not that I would have been unhappy with a table runner that looks like this. It's just that I'd probably be happier with a table runner that looks like this. Isn't that strange how that works out? So anyway, let's look at before and afters for dimensions on these so that we can see how much they've shrunk. So my 8 dent sample here started out on the loom as a nice perfect little square, which is great. I worked really hard on that. And it was 5.5 inches wide. I am talking in inches here. I don't have any inch little symbols, but it's all inches, right? So 5.5 inches wide and 5.5 inches long. After I washed it, and this particularly, I washed it in the way that I would expect to wash the finished result. So because this is, let's say, a table runner, I wanted it to be able to stand up to a washer too, because sometimes stuff gets on your table runners, you need to be able to put them in the washer. So I put it in with the rest of my table linens from home, and I put it on a hot wash and then a dry cycle. So at the end of it, after it all shrunk up, I got, again, a nice perfect square, isn't that wonderful? Of 5.125 inches wide, which is like 5 1/8, something like that. But I want to talk in decimal points just because it's easier to math out. You can always convert them later. So let's just talk in decimals, a little easier to do math. And then my nice perfect square, 5.125 inches long as well, which is so nice. Isn't that wonderful how that works out? It doesn't always work out like that, and we're going to see that here in just a second. So, all right, so brief break for water and also to fix something. Did you catch what my problem was? We're going to talk about the 10 dent now. So my 10 dent sample on the loom was 4.5 inches wide and 5 inches long. And something really crazy happened with this one actually. I think it's because of the way that I tied my knots at the end, but we'll talk about that a little later, but you'll see what I mean. Anyway, my washed dimensions, 4.25 inches wide and 4.5 inches long. See how much that shrunk from 5 to 4.5? That's a lot, that's a ½ inch of shrinkage. So, 12 dent, my tiniest little sample, the one that I like the best. Started out on the loom as 4 inches wide and 3.5 inches long. Look at that. Done it again. Ignore that, it's long. Wash dimensions are 3.75 inches wide and 3.25 inches long. So you can see these things contracted, not a whole lot, with the exception of the length on my 10 dent. I still don't really know why that is. I think it was user error, but we're not gonna worry about that too much right now. We'll talk about that in our next fun math-filled segment. But you can see how they all start to shrink just a little bit. This one just so happened to shrink perfectly into a square, which I love to see. They don't always do that, and that's why it's important to make your samples and take notes of that sort of thing, and also to be sure that you, when you're working on them, to do it with care. To take care with your samples. Don't just slap them on there and then kind of, do your thing and then you just kind of get it off and then you get it, because you're not going to get the end result that you might get out of your finished project. And that might be wider than you expected, or shorter than you expected, or any number of things. So be sure to take just the same amount of care with your sampling that you do with your finished projects. So, I have all of these dimensions. How on earth do I figure out what my shrinkage rate is between this and this? How do I know, but is it 15%, 10%, what? And here's how. All right, here comes the fun part. I know that this looks really scary, and it's not fair to call it scary, but it is a little more complex than what we were talking about before. So, as you can see, we have a compound thing going on here. We've got the on-loom measurement, whether it's width or length. I'm just using the word measurement as a placeholder here. You will do it once for width and once for length to get the shrinkage of both. So, on-loom measurement minus your washed or finished measurement, whether you wash it in the washing machine, if you steam it, whatever. And you're going to divide that number that you get when you take those two things away, by your on loom measurement again. And you're going to take that number, you're going to multiply it by 100, and that's how you get your shrinkage rate. So I know this is a lot, and I just have this here for reference so that we're going to do some more math, hooray. We are going to do this in steps so that we can kind of take it bit by bit. And then when you look at this later on as this whole equation here that is laid out the way that it should be mathematically, it'll make a lot more sense. So let's break it down into 3 different steps, and we'll take them as they go, and we'll get our shrinkage rate and see what happens. Alrighty, so step 1. It's already written up here for me, so let's just take it this piece. Step 1 is to do this part right here, the on loom measurement, whichever one I'm talking about. Let's do width first, just for fun, minus our washed measurement. Okay, so we just talked about this whole big equation. Let's just take it in pieces. So the first thing that we need to do is this piece up here before we can go anywhere else. Let's do our on loom measurement. We'll do width to start, minus our washed measurement, or finished, however you finished it. So for mine, for my 8-dent little sample here, just so happens to be a square, so I'm only really going to have to do this once. My answer for my width is going to be the same as my length because it was a square both before and after, which is great. So step 1, 5.5, which is my width, minus 5.125, which is my width again, but washed, equals 0.375. So our answer up here is 0.375. So this whole bit here can be replaced with this number. But since we're doing this in stages and steps, let's go ahead and take the next step. Okay, so step 2. We did step 1, and we already figured out that these two whole business up here we can replace with a number. So we have 0.375. That is the number that goes above this other thing that we have to do. So that means we have to divide 0.375 by a larger number. And that is our on loom measurement, width in this case. So let's go ahead and take 0.375 and divide that by 5.5, which is our width. And we get 0.06818. It seems like a lot, I know, but bear with me, it gets a little easier later. So now we know that this whole piece here, this whole thing, can be replaced by a number yet again. And it is replaced by 0.06818. So that is step 2. Final step. It's not so hard, right? So, since we decided that this whole mess can be replaced by a number now, which is 0.06818, seems like a lot, we are going to now do the last step, which is multiplying this number by 100. Sounds a little familiar to what we were talking about, dividing by the reciprocal, right? I know. So, 0.06818 times 100 gives you 6.818. Well, what that means is that more or less our shrinkage rate is 6.8, 7-ish%. Give or take. So that's how you figure out shrinkage. In my case, because my sample just so happened to shrink up into a perfect little square, which is wonderful, I don't have to do this twice. I know that my shrinkage both width-wise and length-wise is the same. It's going to be a little less than 7%, which is great. But what happens if that changes? What happens if it didn't shrink into a perfect little square? Then what? And then you have to do it twice. So let's do it twice. Alright, so this is a new sample now. So this is my 10-dent sample, and there's actually some really interesting stuff going on with this one, which I'm really happy about. This will explain things a lot differently. So, once again, we're going to start with our width. Because this is not a perfect square, I am going to have to do this twice. I'm going to have to do this whole situation for my width shrinkage rate and then also my length shrinkage rate. And they actually turn out to be very different. There's a lot of reasons that might be. But let's go through this whole process step by step and see how it all works out math-wise. Step 1. We did this part here, right? Just like we did last time. On loom measurement, width in this case, I'm just going to say width from now on. On loom width minus our washed width. So we've done this. 4.5 minus 4.25 equals 0.25. So what we have here, we've decided already, just like we said before, we've replaced all of this mess up here with a number now. So that is now 0.25. And that's what all of this up here is, right? So now we can move on to the next part. Step 2 is to do this number here that we figured out divided by our on-loom width. So let's do that. 0.25 divided by 4.5 gives us 0.055555 repeating. So for the sake of ease, we're just going to stick with 0.0555, and that's enough. It's actually more than enough. So we've decided that this whole mess is figured out. So let's replace it with a number. 0.0555. Fives are hard to write. So now, we're on the last step, last leg of the race. We figured out this whole mess is now a number, 0.0555. So let's multiply that by 100, shall we? 0.0555, how many times am I going to say that? Times 100 gives us a shrinkage rate of 5.55. So we're looking at 5.5% shrinkage rate. If you want to be really super accurate, you can take into account all of these 5 repeatings if you want to. But honestly, it's going to give you some crazy number that you just absolutely can't get to. So it's okay to round just a little bit. So it's 5 repeating. If you want to jump up to 6% and just have a tiny little bit more than we're really calculating for, that's okay too. But if you want to stick with 5.5-ish%, that's also fine. Somewhere in that realm of doing it by quarters or something like that is totally reasonable. Getting crazy with all of your decimals really is not reasonable. I'm doing it for the sake of math here. And just like we saw before, it really all works out in the end. We ended up with 6.8 last time, which is really easily rounded up to about 7%. So that's how that all works. Rounding up just a tiny bit is really not a big deal, especially when shrinkage is involved. It's really not a problem at all. So 5.5% is our shrinkage rate for our width here, right? So what about our length? The width here that has shrunk, you've seen, is about 1/4 of an inch in width. And it shrunk considerably more in the length. That's a whole 1/2 inch in the length. It doesn't seem like much, especially because, in such a tiny little sample, 1/2 an inch to 1/4 of an inch is really pretty similar. But in terms of shrinkage rates, it works out really differently. So let's do all of this again for our length. Okay, we've done it again. So let's go through everything. You will see that the end result is a lot different, And we'll talk about that. So step 1, let's replace this mess up here above our line, yeah? 5, which is our on-loom length. We're doing length this time. 5 minus 4.5, which is the length after it was washed, equals 0.5. So let's replace this top number here, or this top mess here, with a number. 0.5. I love when things work out so nice and whole like that. Oh, anyway. So now, let's do the second half. Let's do this top part divided by our on-loom measurement. So our top part is 0.5. Stick it right here. Divided by our on-loom length, which was 5. And that gives us 0.1. Isn't that weird? 0.1. All right, so this whole mess has been replaced yet again with 0.1. So now I only have one step to go, and that is to multiply that by 100. And because things work out so easily, we already know what the answer is just looking at it. And it is 0.1 times 100 is 10. And that means that my shrinkage in the length of this particular 10 sample, was 10%. So, looking at both of them together, let's use black, shall we? Our width shrinkage rate, somewhere in the realm of 5.5. It's actually a tiny bit more than that, but we're going to round down to something nice and even. 5.5%. Great. My length, still not sure why, it's 10%. So why is it, or why could it be, rather, because I really don't know the truth of it. Why could it be that this is double that? And the reason is, like I had mentioned before, I've mentioned in the packet a couple of times about how the way we do things is very much like a fingerprint. Nobody's way of doing things is exactly precisely the same as somebody else's. Even if you learned from them, the way that you do it individually by yourself, just by merit of being a whole different person, is going to be different. It might be different by a hair, it might be different by a ton. This is why sampling is so important, because the likelihood that this was user error honestly is pretty high. It was probably something goofy that I did that I don't know what it was. Maybe I tied my knots really far away and that gave it time to shrink up, or maybe I tied them really close and it just kind of compacted everything. Maybe I had tension differences and I wasn't paying attention very well. It could be any number of things. It could just be, I don't know, fate. I don't know. But what this also proves to me is that taking care when making your samples, the same amount of care and you know, attention to detail, I guess, as when you're making your finished product is going to give you the most accurate result. This is probably not super accurate to what my end result would be. I would take a lot more care with my end result to get to something that makes a lot more sense. I wouldn't tie my knots so carelessly if I was making my finished product. So I should take care when I make my sample to do the same. So I have evidence in front of me that my shrinkage rate in this case and the length was 10%. I can't deny that. I have measurements to prove it. But the likelihood that it was actually 10% because of the shrinkage rate of things and the weave structure and all of that jazz is probably not the case. It was probably user error. So, just something to bear in mind. But yeah, let's do this again. And since we've worked this out in stages up to now, let's be adventurous and try to do this kind of all in one go, just like how this is written out up here. And we're going to do that for my 12-dent sample. Okay. Looks different, huh? So let's also, we're still doing this sort of in stages, but again, this is the same thing that we've already done. We're just kind of squishing it all together, just like it's written out in the big, scary equation, right? So we have got our we're doing width again, on loom minus washed, and that gives us 0.25. We are going to take 0.25 and divide that by 4, which is again our on loom, and that gives us 0.0625. So we take that and multiply it by 100, and there we get our shrinkage rate. Ta-da! See, it's not nearly as scary. Just plugging numbers in and then doing a little, you know, just doing a little PEMDAS, actually. And there you go. So, ta-da! So, 6.25 for our width. Let's do it for our length. Length time! So we have our width shrinkage already, 6.25%, just like we said. So let's do it for the length, shall we? On loom minus washed gives us 0.25. Just so happens to work out the same. Weird. Let's divide that by our on loom again, 3.5. And that gives us a funky number, 0.0714. So multiply that by 100, and that gives us 7.14. So just like we were talking about before, there's no sense in trying to get that precise with your shrinkage rate. I genuinely can't think of a time in which you would be that precise. So let's go ahead and round down to 7. It's really close to 7%. So we are going to say that our length shrinkage rate is 7%. See how much closer those are than the one that we had before? That proves to me, especially because the other one, the 8-dent, the first one we did, was also fairly close. There's a little bit of difference, and that's normal. But that's what makes me think that that 10-dent was something that I did. I don't know what it is, probably won't ever know what it is, and that's okay. But that's why it's important to calculate things like this. And that's also why if you want to consider doing like an average of those things, just add them all up and then divide by the number that you had. So in my case, it would be 3 samples. And so it would be that number, all of those numbers combined, divided by 3, and that's my average, right? And so then an average shrinkage rate of this is probably somewhere in the realm of 6.5% to 7%, I would say, just off the top of my head. So yeah, that's what we're looking at for this. Not only these individual rates for these individual samples, but for the overall look and feel of the yarn in a plain weave, I can expect probably something like a 7% shrinkage rate. So here I am again, not being super exact by the end of it. So what's the point in doing all of this really exact math? And the answer is, A, to build good habits. It's good to know how these things work. I am the type of person that if I don't understand how something works or why it is that we have to do it a certain way, I have a really hard time understanding where all of my answers are coming from. Where does this 3.5 come from? Why is it 0.0714? Where the heck did that come from? When I understand why it is that these things come from this and how to calculate things down to a decimal point, then I understand and I can go, okay, I'm comfortable enough with my understanding of this now, getting 7.14, that I can just round down to 7, and it'll be okay. So I hope that helps. I know that shrinkage is a lot, but now you know not only how to calculate your shrinkage rate if you have a finished versus an unfinished dimension of the two on the loom and off the loom, but you also know how to take this number and then go back and divide by the reciprocal. So you're on your way.